Okay, so welcome to this next video on calcium and cyclic AMP oscillations. Okay, so that is how adenylyl cyclase 8 is activated by calcium. Adenylyl cyclase 1 is slightly different. It does not have this calmodulin recruitment domain on the N-terminus, and it doesn't have this transfer of the calcium calmodulin complex from one place to another place. Instead, the calcium apocalmodulin initially binds to this C1b region here. So in adenylyl cyclase 1, and I might just redraw it out. So here's our adenylyl cyclase 1 here. Basically, what happens in adenylyl cyclase 1 is that the apocalmodulin binds to this C1b region here. So this is C1b, and I'll just draw the phospholipid bilayer there. And basically, when the calcium goes up in the cytoplasm, this apocalmodulin transforms to a calcium calmodulin complex, and it remains bound at C1b. And that then causes some sort of conformational change that promotes the dimerization of the C1a region with the C2a region, which are the two halves of the active adenylyl cyclase enzyme. So when they dimerize, you'll get the active adenylyl cyclase enzyme. That will start breaking down ATP into cyclic AMP and inorganic and pyrophosphate. And cyclic AMP goes up when calcium goes up. So both of these adenylyl cyclases, adenylyl cyclase 8 over here and adenylyl cyclase 1 over here, are activated by calcium going up, basically. And that means that when calcium goes up, you'll also get cyclic AMP going up. So this is a mechanism by which you can get phasic oscillations of cyclic AMP with calcium oscillations. Okay, so now what we'll do is we'll turn our attention to antiphasic oscillations. So how do you get antiphasic oscillations of cyclic AMP with calcium oscillations? So one of the mechanisms is through calcium-activated phosphodiesterases, basically. Okay, and the specific phosphodiesterase enzyme, which is calcium activated, well the main one at least, involved in breaking down cyclic AMP, is phosphodiesterases in the family of phosphodiesterase 1s. So remember, there are many different genes coding for phosphodiesterase enzymes, and we can categorize them into 11 different families, i.e. phosphodiesterase 1s through to phosphodiesterase 11. Now, in each family there are separate genes. So in phosphodiesterase 1 family there are actually 3 different genes which code for these calcium-sensitive activated phosphodiesterases. And basically they're all very similar. So when calcium goes up, what happens is that calcium will bind to calmodulin, and you'll then get calcium calmodulin complexes. So if this is a calcium calmodulin complex here, the calcium calmodulin complex goes and binds with the phosphodiesterase 1 enzyme. So this is the phosphodiesterase 1 enzyme here. Diesterase 1 enzyme, and I feel like I should write out the full name. Phosphodiesterase 1. Diesterase 1 enzyme. Right, okay. When the calcium calmodulin complex binds to the phosphodiesterase 1 enzyme, it changes the conformation of that phosphodiesterase 1 enzyme, and this enzyme becomes activated. And basically what it does is it takes in cyclic AMP here, and it breaks the link between the between the phosphate group and the third carbon, basically. It breaks the cycle, basically, and converts it to just AMP, adenosine monophosphate. Okay, so it breaks that link between the... Let me just draw it out. Well, I'm not going to draw the full structure because that takes far too long. But if this is the ribose sugar here, here's the adenine organic base, then basically what you have is your carbon up there, and then you have this phosphate group linked to the 5th carbon and also to the 3rd carbon, and that's cyclic AMP. And basically what you do is you break this bond here to get basically AMP, which is just ribose with its adenosine, with its adenine rather, and then the phosphate group up here, basically. So you break that link between the phosphate group and the third carbon of your ribose sugar to create adenosine monophosphate rather than cyclic adenosine monophosphate. Okay, right, so when calcium goes up, you're going to get an increase in the activity of these enzymes, and what they will do is they'll break down cyclic AMP, so cyclic AMP levels will go down. So that explains, that's a mechanism by which you can get antiphasic calcium and cyclic AMP oscillations, i.e. when calcium goes up, cyclic AMP goes down. Right, so there's a mechanism of antiphasic calcium oscillations. There's another mechanism of antiphasic calcium oscillations, which is that calcium can inactivate certain adenylyl cyclases. So we've seen that two adenylyl cyclases, adenylyl cyclase 1 and adenylyl cyclase 8, are activated by calcium, but there are also adenylyl cyclases which are inactivated by calcium, and these are adenylyl cyclase 5 and adenylyl cyclase 6. So both of these types of adenylyl cyclases are inactivated by calcium going up. Okay, so if calcium goes up in the cytoplasm, what it's going to do is inhibit these adenylyl cyclase 5s or adenylyl cyclase 6. And I just want to briefly go over how that happens. So if we draw out the structure of our adenylyl cyclase, okay, and I'm going to draw the adenylyl cyclase activated, so I'm going to draw it with the C1a and the C2a portion dimerized. Okay, so here is our transmembrane domain 2, then we have our C2 terminus, and here is our C1a portion, here is our C1b portion, here is our C2a portion here, and as you can see I've drawn them nice and close together so that that's meant to indicate that they are dimerized. Okay, so here and here are the active enzyme, basically. They've dimerized. And right at the center of this active enzyme, what happens is a magnesium ion is coordinated. So this circle that I've drawn right in the center there, that is supposed to indicate a magnesium ion. So this is a magnesium cation right at the center of the active adenylyl cyclase enzyme. Okay, and the job of that magnesium cation is when ATP comes in. So remember, the adenylyl cyclase enzymes, its job is to take in ATP and convert it into cyclic AMP and pyrophosphate. So let me draw that out briefly. So here is ribose of our ATP. Here is the adenine organic base, and then you've got 3 phosphate groups up here off the 5th carbon. That's ATP. That's a nice little diagram for ATP. And basically what this enzyme is going to do is it needs to take in this ATP, and these 3 phosphate groups of this ATP molecule here, they have negative charge. So it's actually this magnesium cation which coordinates them, basically. It binds to these phosphate groups, and it is what brings in this ATP molecule. Then what happens is that this is converted into cyclic AMP. So let me draw cyclic AMP again. So here is our ribose sugar, our 5th carbon, and then this phosphate group now linked to the 3rd carbon with the adenine there. And then the other 2 phosphates from ATP that aren't included in this structure, they go off bound together, and that is a pyrophosphate molecule. Okay, right. So this is the reaction basically that this enzyme is catalyzing. Now, once the ATP has come in, it binds with this magnesium ion, this reaction then occurs and the cyclic AMP goes off, and the pyrophosphate also has to go off, basically. The pyrophosphate, remember, both of these phosphate groups have negative charges, so they are interacting with the magnesium ion. What has to happen is that those pyrophosphates have to break off from the magnesium ion, basically, and then empty the active site of the enzyme. Now, that happens usually, but if calcium goes up in the cytoplasm, what happens is that calcium competes with magnesium for the place in this active site. So basically what happens is when calcium goes up, calcium bumps this magnesium cation out and sits there itself. So in comes this calcium ion. It's going to take the place of that magnesium ion, and unfortunately calcium Well, it does magnesium's job okay up until right at the end. So it brings in the ATP molecule, that's just fine, because it's a cation too as well, remember. It's still got 2 positive charges on it. It comes in, it sits in there, it brings in ATP just fine. The reaction happens, you break down ATP into cyclic AMP and pyrophosphate. The problem is that calcium is a bigger ion than magnesium. It's a bigger atom. So it can coordinate, it can bind with more things, because if you're a bigger atom, you've got a bigger surface area, so you can bind with more things. And basically, unlike magnesium, it doesn't lose this pyrophosphate at the end. The cyclic AMP goes off happily, but the pyrophosphate, calcium has an extra 2 binding sites compared to magnesium, and pyrophosphate can remain bound to those extra 2 binding sites that calcium has that magnesium didn't, and therefore pyrophosphate remains in the active site of the enzyme. And when it does, it means that you can't bring in another ATP molecule because the pyrophosphate is in there inhibiting this enzyme. So that means that calcium overall blocks the enzyme because it holds on to this pyrophosphate which blocks the enzyme. So basically calcium can inactivate these adenylyl cyclase 5s and these adenylyl cyclase 6s. So when calcium goes up, it's going to block these enzymes and they're no longer going to produce cyclic AMP, so cyclic AMP will go down, and that's also a mechanism by which you can get antiphasic contractions, antiphasic oscillations of cyclic AMP with calcium oscillations. So overall there are 2 potential mechanisms by which you can get antiphasic oscillations of cyclic AMP with calcium oscillations.